Recording, audio. It's just you and me again. That's okay. Look back at what we covered last time. We started this whole chapter 3, talking about being able to describe data, which means we wanted to come up with measures, quantifiable measures of description. Some people might call figures of merit, which is generally used when they're trying to fudge the fact that it doesn't actually, it's not a really well-defined, it doesn't really mean what we're using it for, but we're calling it anyway. But we want measures, definitively quantifiable measures of the data that describe how it looks, how it's distributed. And the first group we looked at were called measures of central tendency. And I also want to remind you that we talked about the difference between the population and the sample. The population is every member of the group. That doesn't have to necessarily be people. It can be dogs, it can be cereal brands, it can be whatever group is being studied or being described or evaluated. Every member of the group that's of concern is the population. The sample is a subset of that group that is intended as a representation of the population. And I pointed out from the previous chapter that this was an issue on the test and on the homework in particular, that there's a difference between a sampling error and a non-sampling error, and that's probably exactly the opposite of what you would think just by reading the words. Sampling error means that the sample is never going to exactly reflect the population as a whole. Whatever measure of description you calculate of the sample, it's not going to be exactly equal to the population if you calculated that same measure for the whole population. If you calculate that measure for the whole population, it's called a parameter. If you calculate it for a sample, it's called a statistic. And sampling error simply means that the statistic will never exactly equal the parameter. That's the sampling error. That's just a fact of life that we have to live with. Non-sampling error means you messed up the sample. When you selected the sample, when you analyzed it, you did something wrong, and you messed it up. Finally, we looked at 5 or 6, I think 5. The measures of central tendency, our first parameter that we're looking at, parameter or statistic that we're looking at the measures of central tendency. How clustered, how central is the data, or central is the population distributed? How centrally is it distributed? We looked at mean, which is simply the arithmetic mean. Median, which is the middle of the data set. The mode, which is whichever value has the most members in the frequency distribution. The mid-range, which is simply the average of between the minimum and the maximum values in the data set. And then we finally looked at weighted mean for those times when the data doesn't. We looked at it. Today, you're going to start looking at a different measure of data description, or a different set of measures, which is to say parameters and statistics. These are measures of variation. And that means how much does the data vary from its central description, from its central point, from its mean. If we had a population where every member had exactly the same value, then its variation would be 0. Okay? Its range is one value, one class, one category, one value, period. And there's no variation. Every member, of course, at that point, it's kind of meaningless to start talking about statistical analysis, because it's, you kind of got the answer right out of the gate. But that is generally not the case. The example they use in the book is looking at how long does paint last? And they compare 2 different brands of paint from 2 different manufacturers. They list here brand A and brand B. They list 1, 2, 3, 4, 5, 6 different values for how long a gallon of paint lasted once it was applied to whatever surface it was put on. Brand A had one of their gallons lasted for 10 years, one gallon lasted for 60 years, another one lasted for 50, 30, 40, and 20. And then brand B lasted for 35, 45, 30, 35, 40, and 25 years. And it shows there in the example that if you compare those two and ask which one lasts longer, then the answer, if you look at the mean, then you get 35 months is the average for both of them. And that might suggest, well, there's no difference. They're both going to last an average of 35 years. But is that true? Is it true that there truly is no difference? Well, let's look here at the way they do it graphically. They start with brand A. One lasted 10 years. One lasted 20 years. One lasted, say again, 30. What's the next one? And 60. Okay, and the average value was right here at 35. But how does that compare to brand B? Well, brand B had one that lasted 25 years. One that lasted 30 years. Two that lasted 35 years. And then 40 and 45 years. Well, you can, without doing any numerical analysis, look at that picture and see that there is a significant difference in the life expectancy for either one of these. Okay, you go with brand A, and you're just as likely to have it last less than 35 years, possibly significantly, as you are to have it last more than 35 years, possibly significantly. If you go with brand B, it's not very likely that it's going to last significantly less than 35 years. It's also not likely that it's going to last significantly more than 35 years. But you're going to be a lot more assured that you're going to get a lot closer to 35 years of life out of it. And that's the whole point of variation. The first measure of variation that we're going to look at is the parameter and its associated statistic of range. Well, that's a very simple one. The range, Jordan, welcome, willkommen, bienvenue. If we look at brand A, the range for any of them are is equal to the maximum value from the minimum value of the data set. So for brand A, it's 60 years minus 10 years. Giving it a range of 50 years. The range for B, brand B, is going to be 45 years minus, what was the bottom one there, 25 years. At a range of only 20 years. That right there tells you brand B is much more centrally distributed than brand A. Oh, and I used the wrong units. In the book, they're using it in terms of months. Doesn't really change anything. Oh, we're in page 136, 137. We're chapter 3-2. And before we go any further, let me go ahead and ask, do you have any questions from the homework? Either of you? No? So good. All right. So that's range. It's a measure, meaning it's quantifiable. We can calculate it. It is a measure of a parameter and of its associated statistic that we can calculate, and it describes how centrally distributed a data set is. But it's also about the simplest one. And it's kind of limited in its usefulness. It's not an incredibly precise parameter or statistic. It's not a really precise. It's more of a bigger hammer, ballpark kind of calculation than let's see if we can start getting how specific we can start getting. To do that, we're going to have to start looking at something called variance and the standard deviation. Variance is simply defined as the distance of a particular data value from the mean of the data set. whether we're talking about a statistic of a sample or a parameter of a population, each member is going to vary from the mean by a certain amount, and that amount is called its variance. So, the variance, here we've got what, 60, 50, 40, 30, 20, and 10. The variance of this datum is 60 minus 35 is 25 years. Plus 25 years, or months, or whatever. This one is plus 15. This one is plus 5. This one is minus 5, minus 15, and minus 25. So, how do we talk about the variance of the whole set, the whole data set? It doesn't matter whether we talk about this one or this one. By definition, this is the mean. So in every case, if you just add up the variances of all the members of the data set, population or sample, it's always going to sum to 0. But that's not really helpful. That just tells us what the mean is. The mean is where it all sums to 0. To talk about how much the data set varies from 0, we look at the squares of the variances. So in this case, this is 60 minus 35 is 25. And we talk about 25 squared is, somebody with a calculator, help me out. $25 squared. 625, right? All right, what's 15 squared? 225. And 5 squared? And minus 5 squared? Still 25. Minus 15 squared is still 225. And minus 25 squared is still plus 625. Now, when you add them up, they no longer add to 0. So now, the sum of x minus x bar, the mean, squared, is equal to 1750. Now, what does that tell us about the average variance of any one of these data? The average variance of a single datum would be, in this case, let's pretend like this is the whole population. So instead of x bar, we're going to talk about mu. The population. So we're talking about a parameter, not a statistic. And I want to pretend like this is the whole population because we're going to get to us here in just a minute. We're going to find that there's a slight change that we're going to have to make when we do a sample variance. But I don't want to get there yet. So that's the population variance. The average variance for any one datum in the population would be that divided by how many are there. In this case, there's 6 total. So the actual variance of the whole thing is, what, 291 and 2/3. The variance for the population is denoted with the lowercase Greek letter sigma squared. I was asking, what is the average variance for any one of these data? Does that make sense? That the average variance for any one particular datum would be 291? What's the square root of 291? No, the square root. 17.08. Now, this is called the population variance. And it's defined as sigma squared. That's simply the square, the sum of the squares of the variances divided by the number there are. The square root of the population variance is called the population standard deviation. And I ran out of room to keep writing it, but now, all of a sudden, that looks more reasonably meaningful. And any one of these, the average, any one of these might be 17.08 months or years or whatever, deviated from the average of 35 years. What's the average of this? 5 plus 15 plus 25. $15. Okay? And that is why they don't call this the average variance, because it isn't quite. You're going to find that I do this quite a bit in this class, but we're not going to dig deep into the theoretical mathematics behind these equations and formulas. I'm simply going to give you the reasoning behind them. The idea is not for you all to become theoretical statisticians. The idea is for you all to learn how to use these equations in whatever field of study you've chosen. You don't really need the deep theory behind it to do that. But this is why it's called the standard deviation and not the average deviation, because it's not quite the average. And it varies from the average by the fact that the square of the deviation, or the square of the variation, is divided by the number of data in the variation. And then that number is taken as a square root to get to the standard deviation. This, of course, is for the population as a whole. about for just a sample? Well, the sample variance is denoted with the Roman letter s, lowercase s, squared. And the sample standard deviation is denoted with just the lowercase Roman letter s, which is equal to the square root of the sample variance. Just like here. Sigma is equal to the square root of the population variance. Now, how do you calculate the sample variance as opposed to the samples and the sample standard deviation as opposed to the population version? Well, start with x, the value of each datum. Subtract from that the sample mean as opposed to the population mean. Square them. Add all of those together, just like you did with the population calculation. Whereas the sample runs from the population runs from 1 to uppercase n, meaning the n being the number of data in the entire population. The sample only goes up to lowercase n, which is the number of data that you've selected for that sample. Now, that looks reasonable, right? If that's the population, this is the same calculation for the sample. And here is another one of those times when we're not going to go into the deep theory and derive all of this from first principles. But I am going to explain to you why this is not what is used. That in fact, when you calculate the sample variance, you don't divide by n, you divide by n minus 1. And then the sample standard deviation becomes the square root of the variance. Now, why do you divide by n minus 1 instead of n? You got a guess? What about you? Well, yeah, but I mean, why? Why would we treat the sample differently than we would treat the entire population? Okay, it's time to back up to our first principles and remember our objective here. Remember why we're studying this. Populations are generally too large to analyze mathematically, quantitatively, directly. I mean, they're too big, as a rule. So this calculation is just impractical. We can choose a small sample, or a sample small enough to do the analysis, especially with computers, to do all the number crunching. But this goes back to the whole issue of sampling error. Sampling error versus non-sampling error. Heads up, I'm going to repeat this again because this is something that you both and anyone else in the class who's just watching the video needs to put in your mind and keep it there. Sampling error is not this where the statistician made a mistake in choosing the sample. Okay. Sampling error is simply a statement of the fact that the statistic X bar, or the sample mean, is never going to exactly equal the parameter, the mean of the entire population. Okay? It's just never going to happen. They're both measures of central tendency. They're both the arithmetic mean. And the sample is chosen as a representative of the population. But the parameter of the population is never ever going to exactly equal the statistic of the sample. The parameter and its associated statistic will never be exactly the same. That is sampling error. That is the error that is introduced simply because you're not calculating the whole population. Non-sampling error is when the statistician messes up choosing the sample. Okay? And I know that's logically that seems backwards to anyone who speaks English. But if you speak statistician, it makes perfect sense. So, because of sampling error, because the statistic will never exactly equal its associated parameter, and if you think about it, that really does make sense. Because even when you take samples, you see it happens all the time. There are outliers. You take a series of measurements, there's always going to be one or two outliers that are just farther out than the others and stuff. Well, guess what? That happens with the whole population too. And so there's going to be those extra pieces, extra data that are way out at the fringes that your sample just doesn't recognize or reflect. Consequently, if you calculate this just by dividing by n alone, the number of samples in the data set, it's going to under-reflect the parameter that it's intended to reflect. The population standard deviation will always be a little bit bigger than the sample standard deviation. Now, why would that be? Why wouldn't it be why wouldn't it be just as likely to be a little bit less than the sample standard deviation? Think back to why we calculated the variance the way we did. Because if you just add up the variances of all of the data, always going to sum to 0. So you add the squares of the variances to get the population variance. See the square notation? The superscript 2? That means it's always going to be bigger. Okay? So yeah, if you were dealing with just the variances directly, then yeah, the sample variance would be just as likely to be a little bit less than the population variance as it would be to be a little bit larger than the population variance. But you're not dealing with them directly. You're dealing with the squares, which means the population variance is always going to be a little bit bigger than the sample variance. So, instead of dividing by n, we divide by n minus 1, which means this statistic becomes a little bit bigger than it would have been otherwise. And that corrects for the fact that we're dealing with the squares of these variances, not the variances themselves. That makes this a little bit bigger. And that makes this more consistently, more reliably, an accurate reflection of the parameter that it's associated with. Whether we're talking about variance or standard deviation. And that's the reason that you divide it by n minus 1 and not n. Does that make sense to both of you? Any points of confusion here? Okay. No, you got something? Okay. Now I'm going to give you one more bit of information about this. We're in the book, and what I've just told you is that population, you have the mean, and you have variance and the standard deviation. And for the samples, you have the mean, the variance, and the standard deviation. These are parameters measures of the entire population. These are the associated statistics of those parameters. Well, that's just to help you just to help you sort and file all of this away in an organized way so you can keep up with what's going on. Now I'm going to tell you what you're going to run into when you get out of this book and out of this class and you start looking at spreadsheets and other books, and sometimes you're going to find this population standard deviation written as sigma sub n. And you'll find this sample standard deviation written as sigma sub n minus 1. Similarly, you will find sigma squared written as sigma squared sub n, and s squared written as sigma squared sub n minus 1. This is the reason. And that's the distinction that they're making. So if you ever see sigma written with the subscript n, you know it's talking about the population standard deviation or the population variance. And then you will be able to, you'll then know to look out for sigma sub n minus 1, which would be the S version, the sample version. All right. There's a couple of rounding rules I want to mention. They hide them. Here we go. We're not running out of time yet. I still want to talk about coefficient of variation, range rule of thumb, Chebyshev's theorem, and the empirical rule, or the normal rule. I also want to I'm just going to, I don't find it handily in the book, but I'm just going to tell you. When you are calculating the mean of a population or of a sample, especially when you're dealing with a large set, when you calculate a mean, how many decimal places do you round to? How many decimal places? You're closer, but no. You round to one more than the raw data. If the raw data is written in integers, then you round to the first decimal place, the first place after the decimal. If the raw data is in, this is a better way to phrase it. When you're rounding the mean, when you're calculating the mean, you round to one additional significant figure. So do you remember significant figures? Do you? How many significant figures is here? 2. So if you were calculating the mean based on data that had 2 significant digits, then you would calculate it to, you could write this as 15 times 10 to the power of 3, and you would then round it to 15.x times 10 to the power of 3. Right? If your raw data has 15.3, 12.6, 8.1, then you would round to the second decimal place. Okay, but you want to, the point is, you want to add one significant digit to your calculated value. Right? Now, the same rounding rule applies when you're calculating variances or standard deviations for either the population or the sample. Okay. Now, you'll turn to page 146. There we're going to talk about coefficient of variation. Now, despite my getting confused about whether these were months or years, is irrelevant. The fact is, we wanted to compare how long this paint brand lasted compared to how long this paint brand lasted. And we found that, well, we never calculated the variance or standard deviation of this one, but we could calculate it. This one, the brand A, we calculated and found it had a variance of 291 2/3, or a standard deviation of 17.08. We could also calculate the standard deviation of this one, and we would find that it was significantly less than 17.08. In this case, it would be a legitimate comparison because we're comparing years to years. Both data sets are expressed in the same units, so we can just directly compare their standard deviations, their variances, their means. But what if you were comparing 2 different data sets? You wanted to compare their variances or their standard deviations, but they were in different units. What's the example here? Yeah, here he talks about wanting to compare the number of sales per salesperson over a 3-month period as compared to the commissions made by those salespeople over the same 3-month period. Well, now you've got one that's just the number of sales, and you've got a second one that's the amount of commissions they make. Well, if you want to compare their variances, you can't really do that because you're literally, or no, metaphorically anyway, comparing apples and oranges. You're comparing dollars to numbers of sales. So, how would you compare the two? You would compare the two by calculating the parameter or the statistic that you want to compare and then converting it to a coefficient of variance. Okay? So, let's say in the first case, we want to compare the number of sales, and how much that varies. So that would be the standard deviation of sales. How does that compare to the standard deviation of commissions? Units of numbers of sales and units of dollars. Well, before you can calculate sigma, you would have to first calculate the mean. Now, and let me also point out, in both cases I'm using mu and sigma, not x bar and s. Why? Because the entire population are the sales in that dealership and the salespeople in that dealership. That's the whole population. It's the entire thing we're concerned with. We don't care about other dealerships or other salespeople or anywhere else. Because that one little world is the only thing we're concerned with. We don't need to try and sample the salespeople and figure out, and try to extrapolate from that. We can just take the whole population measures directly. So you calculate mu, the mean for the commissions awarded in those 3 months. Here you calculate the mean for the sales. Then you divide the sigma, the standard deviation, or the variance, by the mean to get the coefficient of variance. Same thing over here. Only I wrote sales and should have wrote commissions. You're effectively turning them both into percentages, which means now they are unitless ratios and they can now be legitimately compared to one another. So, coefficients of variances. You either divide S or S squared by X bar, or you divide sigma or sigma squared by mu. Okay, but the point is you divide, you know what? I'm not really certain that that's, let's stick to what they say in the book. For samples or for populations, you divide the standard deviation by the mean, and that'll give you a ratio that you can legitimately compare to another. Now, what was the very first measure of variance, of variation, that we talked about? Was the range. And oh, I've still got it written right up there. There is something called the range rule of thumb. And it holds that a rough estimate of the standard deviation, sample or sigma, is R divided by 4. That's just a very rough estimate. Let's compare it. We found the range of A was 50 years. So by the range rule of thumb, would be equal to 50 divided by 4, which would be approximately 25. Of course, in that case, we actually calculated. And we found that the actual standard deviation, or variance, was 17 and change. Okay? That's a very good comparison right there of the two. Range rule of thumb is only a rough and very rough estimate. Just like the range is only a very rough estimate of the variation of the data around its central. Now, very quickly, I'll give you Chebyshev's theorem and then the empirical or normal rule. Chebyshev's theorem. And it's on page 148 if you want to read it. The proportion of a data set that will fall within K standard deviations of the mean will be at least 1 minus 1 over K squared. 1 over K squared. So if you want to know what percentage of the data set will fall within K standard deviations, then you square K, take the reciprocal, subtract it from 1, and that's your percentage. Or that your percentage will be at least that many. Might be more, but it will be at least that percentage. Now that's the Chebyshev's theorem, and that is true for any distribution, any population, any sample. For any distribution, that will always be true. But in the special case of a normal distribution or a Gaussian distribution, the empirical rule says that %68 of the population of the sample of the data will be within one standard deviation. 95% will be within plus or minus 2 standard deviations, and 99.7% will be within plus or minus 3 standard deviations. That's the empirical rule. That is for the special case of a normal or Gaussian distribution, a bell-shaped curve. Now, you can do some comparisons and you will find that even on a bell-shaped curve, this is still true. It will be this, at least this percentage will be within those standard deviations. In fact, it'll be more in the case of a bell-shaped curve. No matter what the distribution is shaped like, that will always still be true. That is the end of our class. Any questions? Comment? You good? All right. You both know how to find me if you need help. If you got anything that you need to explain more, better, give me a holler.